Intersection of sets introduction. In mathematics, a set is a well-defined collection of distinct objects. Now, what does that mean? Think of a set as a container, but a very organized container. Well-defined means we have a clear rule for what can and cannot be included in the set. Distinct simply means that each object inside the set is unique, no repetitions allowed. For example, a set of the first 5 positive integers would be a valid set, considered as an object in its own right. This might sound a little strange at first, but it's important. We treat these collections of objects, these sets, as single entities that we can work with mathematically. Just like you'd treat a number like 5 as a single entity, we treat a set like 1, 2, 3 as a single entity. When dealing with multiple sets, we often need to identify elements that are common to all of them. Imagine you have 2 sets, one of even numbers and one of prime numbers. If you wanted to know what numbers are both even and prime, you'd be looking for the common elements. This is a very common operation in mathematics. This leads us to the concept of the intersection of sets. The intersection, simply put, is the process of finding those common elements. In the next few slides, we'll define this formally, learn how to find it, and visualize it using diagrams. So, this slide is just setting the stage for what's to come. We'll be building on this foundation as we move forward. So let's begin our discussion on the intersection of sets. Intersection of sets, defining intersection. So now that we've introduced the idea of what the intersection of sets is, let's get a bit more precise in defining it. As we discussed on the previous slide, the intersection of sets deals with finding the elements that are common to all the sets we're considering. This slide formalizes that idea. The first point here states that the intersection of 2 or more sets is simply a set that contains only those elements which are present in every single one of those sets. It's crucial to remember that only part, if an element isn't in all the sets, it doesn't belong in the intersection. Next, we introduce a notation to make things concise. We use the symbol a intersection B to represent the intersection of 2 sets. A and B, think of it as a way to write the elements that A and B have in common in a shorter form. The intersection symbol looks like an upside-down U. So, we say a intersection B. Now, let's look at the formal definition. It might seem a little intimidating at first, but we'll break it down. We write A intersection B equals the set of all x such that x is an element of A and x is an element of B. Let's unpack that. The curly braces denote a set as we've already covered. The x represents a general element. The symbol is an element of means belongs to, so x is an element of a means x belongs to set A. The such that part, represented by the vertical bar, acts like a condition. It's saying, consider only those x's that satisfy the following condition. In this case, the condition is that x must be in set A and x must also be in set B. Essentially, this formal definition is just a fancy way of saying that the intersection contains all the elements that are members of both A and B simultaneously. We'll see how this works in practice with examples on the next slides, using both listing the elements and visualizing with Venn diagrams. But understanding this definition is key to understanding the whole concept. Intersection of sets determining intersection, roster form. So now we're going to work through some examples to really solidify our understanding of how to find the intersection of sets. As we discussed on the previous slides, the intersection is all about finding the elements that are shared between 2 or more sets. We'll be using what's called roster form here. This simply means we'll list out the elements within curly braces. That's how we represent sets, remember. Let's look at our first example. We have 2 sets, set A and set B. Set A contains the numbers 1, 2, 3, 4, and 5, and set B contains the numbers 3, 5, 6, and 7. Now, to find the intersection of A and B, which we write as an intersection B, we need to identify the elements that are present in both A and B. We'll do this systematically. We'll take each element from set A, one by one, and check if it's also in set B. So let's start with the number 1. Is 1 present in set B? No, it is. Next, let's check the number 2. Is 2 in set B? Again, no. Now let's look at the number 3. Is 3 in set B? Yes, it is, so 3 is a common element. Moving on to 4. Is 4 in set B? No. And finally, let's check 5. Is 5 in set B? Yes, 5 is also in set B, so 5 is another common element. Therefore, the elements that are common to both set A and set B are 3 and 5. So we write the intersection of A and B, A intersection B, as the set containing 3 and 5. In roster form, that's written as 3, 5. This is a crucial step-by-step process. We'll build on this in the next examples, including using Venn diagrams to visualize this, and also looking at how to find the intersection of more than 2 sets. But for now, make sure you understand how we methodically checked each element to find the common ones. Intersection of sets determining intersection. Roster form, example 2. Let's move on to another example to solidify our understanding of set intersection. Now on this slide, we have example 2. We are given 2 sets, set C and set D dollar. Set C dollar contains the elements B, C, and set D dollar contains the elements E, F, and G. Take a moment to look at these 2 sets. Can you identify any elements that appear in both C dollar and D dollar? That's right, there are no common elements. None of the letters in set C dollar are also found in set D dollar, and vice versa. When 2 sets have no elements in common, their intersection is called the empty set. We denote the empty set with this symbol, which looks like a slightly curved 0, and we call it the empty set. So, in this case, the intersection of C dollar and D dollar, written as C intersection D dollar, is equal to the empty set. We write that as C backslash cap D equals backslash empty set dollar. This is an important concept to grasp. It shows that not all sets have to share elements, and when they don't, their intersection is simply nothing, the empty set. Remember this as we move forward, because in the next slides, we'll be visualizing these intersections using Venn diagrams, and understanding the empty set will be crucial for interpreting those diagrams correctly. Intersection of sets determining intersection. Venn diagrams. So far, we've been finding the intersection of sets by carefully looking at the elements and listing out what's common. Now, let's explore a more visual approach using something called Venn diagrams. Venn diagrams provide a visual way to represent sets and their relationships. Think of them as a helpful picture to understand what's going on with our sets. Typically, we use overlapping circles to represent sets. Each circle represents a set, and where the circles overlap is key, that overlapping region represents the intersection of the sets. Remember from the previous slides, the intersection contains elements that are present in all the sets we're considering. Let's look at an example. We'll call it example 3. Let's define 2 sets. Set A contains the numbers 1, 2, and 3, and set B contains the numbers 2, 3, and 4. Now imagine drawing 2 circles. Draw one circle and label it A. Then draw another circle that overlaps with the first one and label this one B. The area where these 2 circles overlap represents the intersection of A and B. That is, A intersection B. Now, let's identify the elements that are in both A and B. Looking at our sets, we can see that the numbers 2 and 3 are present in both A and B. So, we place the numbers 2 and 3 right in the overlapping region of the Venn diagram. This visually shows us that these are the elements that belong to both sets. Next, we have the elements that are unique to each set. The number 1 is only in set A, so we place it in the part of circle A that doesn't overlap with circle B. Similarly, the number 4 is only in set B, so we place it in the part of circle B that doesn't overlap with circle A. Visually, you can now clearly see that the intersection of A and B, that is, A intersection B, is the region where the circles overlap, and it contains the elements 2 and 3. So, A intersection B is equal to the set containing 2 and 3. This is a really useful way to visualize intersections, especially when dealing with more complex sets. In the next slide, we'll see how this concept extends to even more than 2 sets, but this diagram will help us keep things clear. Intersection of sets, intersection of multiple sets. So far, we've been looking at finding the intersection of two sets, the elements they have in common. Now, let's move on to something slightly more complex. This slide shows us that the idea of intersection isn't limited to just two sets. It extends to any number of sets. So, if we have three sets, let's call them A, B, and C. The intersection of all three, which we write as an intersection B intersection C, consists of all the elements that are present in all three sets simultaneously. Think of it as a stricter condition than finding the intersection of just two sets. Let's look at an example to make this clear. We're given three sets. A contains the numbers 1, 2, 3, and 4. B contains 3, 4, 5, and 6. And C contains 4, 5, 6, and 7. Now, to find the intersection of all three, a intersection B intersection C, it's often easiest to work step by step. We first find the intersection of two of the sets, and then intersect that result with the third set. In this case, let's start by finding an intersection B looking at sets A and B. We see that the elements they have in common are 3 and 4. So, a intersection B is the set containing 3 and 4. Next, we need to find the intersection of that result, which is 3, 4 with set C. So, we're looking for elements that are in both 3, 4, and C, which contains 4, 5, 6, and 7. The only element present in both of those sets is 4. Therefore, 3, 4 intersection C is simply the set containing 4. And that means at intersection B intersection C, the intersection of all three sets is equal to the set containing just the number 4. So remember, when dealing with multiple sets, the intersection only includes elements present in every single set. This is a crucial point to remember, and we'll reinforce this as we move forward. Intersection of sets key takeaways. First point, the intersection of sets contains only the elements common to all the sets involved. Remember, when we're finding the intersection, and we denote it by saying a intersection B, we're looking for what the sets share. If an element isn't in every set we're considering, it doesn't belong in the intersection. Next, we can determine the intersection using what we call roster form. This simply means we list out the elements that are common to all the sets, enclosed in curly braces. We saw this in action with our examples, carefully going through each set and identifying the elements that appeared in all of them. Then, we explored how Venn diagrams can be incredibly helpful. They give us a visual way to understand the intersection. The overlapping region of the circles represents exactly that, the elements that are present in all the sets. It's a great way to see what the intersection is, especially when dealing with more complicated scenarios. Finally, and this is important to remember, the concept of intersection isn't limited to just two sets. It extends to any number of sets. We even saw an example with 3 sets, where we found the elements present in all 3. You can apply the same logic to 4, 5, or even more sets. You just need to be systematic in checking for common elements. Let's recap everything we've learned about the intersection of sets. This slide summarizes the key takeaways, and it's important you have these firmly in your mind before we move on to practicing more complex problems. So, keep these 4 points in mind as we continue. Understanding these core ideas will make tackling more challenging problems much easier. On the next slide, we'll look at some common mistakes students make when working with intersections, so we can avoid those pitfalls. Intersection of sets, common mistakes. First, a very frequent error is including elements that are not in all sets. Now, remember from our earlier discussion, the intersection, and I'm referring to finding an intersection B, means we're looking for the elements that are present in every single set we're considering. So, if an element appears in only some of the sets, but not all of them, it absolutely cannot be included in the intersection. It's a strict requirement. Next, let's address confusing intersection with union. This is a classic mistake. We've talked about both, so let's quickly recap. The union of 2 sets, written as a union B, includes everything from both sets, all the elements combined. Think of it as merging the 2 sets into one bigger set. The intersection, a intersection B, on the other hand, is much more selective. It only includes the elements that are found in both sets. So, Union is all, intersection is common. Keep that distinction clear in your mind. Finally, let's talk about incorrectly interpreting Venn diagrams. We saw how useful Venn diagrams are for visualizing sets and their intersections. Remember, the overlapping region of the circles represents the intersection. It's the area where the sets share elements. It's easy to get distracted by the entire circles, but when you're identifying the intersection, focus solely on that overlapping part. That's where the common elements reside. Let's move on to the final slide, where we discuss some common pitfalls students often encounter when working with the intersection of sets. This is really important, so pay close attention. So, those are the key mistakes to avoid. By being mindful of these points, you'll be well on your way to mastering the concept of intersection of sets. And that brings us to the end of this tutorial. Remember to practice these concepts with various examples to solidify your understanding.